All right, everybody, this is 6.3, Trigonometric Equations. The book labels it as Part 2, all right? 6.2, the previous video was Part 1, so here's Part 2. You'll notice that all of the trig equations in this section have something in common, and that is the argument is being manipulated. Some of the arguments are half angles, some of the arguments are double angles, and things like that. Let's take a look at our first example. Okay guys, example 1, solve the equation 2 times cosine of x over 2 minus root 2 is equal to 0. See, this argument right here is what I was talking about. Here in part 2, in 6.3, in this section, all of the arguments are like half angles like this or double angles and so forth. We didn't see this kind of thing in the first part in 6.2. So look out for this. But keep in mind, we are solving for x here. The argument happens to be x over 2, but we're solving for x. And there's two parts to this. We're going to first solve this equation for x over the interval 0 to 2 pi. Okay? That's the first part of this that we're going to do first. And then after we're done with that, we'll go to the second part, which is solve for all solutions. Okay? So let's go for this first part, part A, solving the equation over the interval 0 to 2 pi. Let's go. Okay, my first thought is to isolate the function, is to isolate cosine of x over 2. So I'm thinking we should add root 2 to the other side, and when we're done adding root 2, then we'll divide both sides by 2. Okay, when you add root 2 to the other side, then you get 2 times cosine of x over 2 is equal to positive root 2. And then when you divide both sides by 2, you get cosine of, you get cosine of x over 2 is equal to root 2 over 2. All right, very good. Now, I want to draw your attention to something over here maybe. We know that we're solving for x, right? And we also know that x has to be between the intervals 0 and 2 pi. All right, we know this relationship with x. But the question is, what about x over 2? Where is that coming from? Where does x over 2 live? What's the interval for x over 2? Well, if you divide x by 2, then you should divide 0 by 2, and you should divide 2 pi by 2. So when you divide 0 by 2, you still get 0, and when you divide 2 pi by 2, you just get pi. So when you and I consider answers right now, when you and I consider x over 2 and what the possibilities for that argument could be, we can only look at between 0 to pi, basically quadrants 1 and 2. Okay, I can add that. This is basically quadrant 1 and quadrant 2. All right, everybody? All right, cool. Let's move this up. And let's continue. Because of our knowledge of our unit circle and how well we know it, in quadrant 1, we know that cosine of x over 2 will be root 2 over 2 if you're taking cosine of pi over 4, right? What I just said right there is, I said if x over 2, if that is pi over 4, I know this will work. Cosine of pi over 4 will be root 2 over 2. Now, in quadrant number 2, we don't have an answer. And the reason why is because in quadrant number 2, cosine values are negative. So this is the only answer I'm going to get. So what I should do here is multiply both sides maybe by 2 to isolate x, right? Because then you'll get this x, that 2 and that 2 to divide out. And then, of course, we also know that 2 divides into, I guess I'm using red right now, right? So 2 divides into 4 twice right there, right? So what we have then on the left is just x isolated, and we get x is equal to pi over 2. All right, everybody? Oh, you know what we should do? We should be a little more formal with our final solution. And what I mean by that is let's use set notation. That would be really good. So set notation just means use braces. So our set of solutions is just pi over 2. And you can close your set. That's better than just boxing x equal to pi over 2. Hey guys, I wanted to bring something up to your attention. When we were over here thinking about cosine of what gives me root 2 over 2? Cosine is also positive in quadrant number 4, right? Quadrant 2, you're negative. Quadrant 3, you're negative. But in quadrant 4, you're also positive. So watch this. If we let x over 2 be 7 pi over 4, this will also work, right? 7 pi over 4. Cosine, I'm saying that if x over 2, if the argument is 7 pi over 4, cosine of 7 pi over 4 is also root 2 over 2. It seems like it works. However, when you solve for x here, watch what happens. Let's multiply both sides by 2, right? Multiply both sides by 2, and you can cross cancel, right? So then this is x is equal to 7 pi over 2. Now what's the problem of that? The problem is this proposed solution is not between 0 and 2 pi. This solution is greater than 2 pi. So this is outside the range, right? So all of this is invalid. Which is why I took you down this road over here. Excuse me. I said that when we consider our values for x over 2, only look at values between 0 and pi to make sure that you are, at the end of the day, giving an x value that is between 0 and 2 pi. When you and I just pulled an x over 2 value that is in quadrant 4, when we just considered x over 2 greater than pi, our final answer ended up being greater than 2 pi for x. So this interval right here is really important, all right? Now for part B, remember it says solve for all solutions. Look at your argument in your equation that you solved. Your argument is x over 2. That implies that, do you remember when we were in chapter 4 graphing our functions? That implies that the period, right? The period. Do you remember in chapter 4 saying that the period is 2 pi over b? Well, your b value here is 1/2, right? So your period is 4 pi. That means your function values, your answers, will start to repeat, right? Because these are periodic functions, every 4 pi. So let me see if I can give you a picture to visualize, all right? Now, one answer turned out to be pi over 2, right, everybody? That was an answer. The other proposed solution turned out to be 7 pi over 2. Now this is 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So the other proposed solution that we ended up not being in the correct interval is 7 pi over 2. Right? And the other one was pi over 2. Now watch this. What we just figured out with the period being 4 pi is pi over 2 is a solution for this equation. And then you hit another solution when you go, that's 2 pi and 4 pi. Did you catch that? I could show you this here. When you start with pi over 2 and you go 4 pi, you just hit a brand new solution. If you go to another 4 pi, you get another solution. Go another 4 pi, you get another solution. So there's infinitely many solutions, right? Now watch this. If you start at 7 pi over 2 and go 4 pi, right? Let me start right here, smaller here. Actually, let me go back. If you start at 7 pi over 2 and go 4 pi, there's a solution, right? Now, you may be thinking, wait a minute, we threw 7 pi over 2 aside, like we didn't use it. I know, but because in part 1, everybody, if I can scroll up here, there we go. If I can scroll up, in part 1, it was very important that we were only looking at x values that are between 0 and 2 pi. But now in part B, we're solving for all solutions, not just for the solutions that are between 0 and 2 pi, but for all solutions. And one of those solutions that we threw aside, 7 pi over 2, now can be considered because we're solving for all solutions. So, there we go. So these are our solutions. We're going to write our final answer like this. Set notation. Pi over 2 plus multiples of the period. So it'll be 4n pi, where n is an integer. Okay? And the other solution will be 7 pi over 2 plus 4n pi. If I could just write this, that'd be good. Okay. All right, got it. There's our final answer. All right, everybody? Cool. Let's look at the next example. All right, guys, example 2. Solve cosine of 2x is equal to sine x over the interval 0 to 2 pi. There's only one part of this. There's no two-part process to this because they are not asking for all solutions. They're just asking for the solutions that are between 0 and 2 pi. Okay, guys, my first instinct is to work with that left-hand side. It's a double angle. And to make it, when I think about my double angle identities for cosine, I remember that there's 3 different ones. But there is one identity for the double angle identity for cosine. There's one of them that is only in terms of sine. So let me see if I can remind you that cosine, this is the original equation. Cosine of 2x is the same thing as 1 minus 2 times sine squared of x. That's what that left-hand side is equal to using a double angle identity. The cool thing about this equation now is that this is all in terms of sine. Everything is in terms of sine. If you set this whole equation equal to 0, I think you'll be in good shape. So you have positive 2 sine squared x plus sine x, and then minus 1 when you set this equal to 0. All right, cool deal. Now, I think this factors, if I'm not mistaken, 2 times sine x, and then a sine x here. And I believe we want a plus 1 out here, and then a minus 1 in here. Yeah, that'll work. And then you know from your algebra studies that you set each factor equal to 0 and solve, right? When you set each factor equal to 0 and solve, over here you will get sine of x is equal to 1/2. Of course, after adding 1 and dividing by 2. And over here, you'll get sine of x is equal to -1. Okay, now, we're just about done, but I want you to think about your unit circle. And when is sine positive? When is sine positive? Sine is positive in quadrant 1 and in quadrant 2. That's it, okay? When you think about sine of x equal to -1, sine is -1 at only one time on the unit circle. So let's go to sine of x is equal to 1/2. In quadrant 1, this will occur if x is pi over 6. In quadrant 2, this will occur, sine of x will be 1/2, that is, if x is 5 pi over 6. Okay? For this one, over here, sine of x will be -1. That will be true if x is 3 pi over 2. All right? So in set notation, you'll have pi over 6, 5 pi over 6, and 3 pi over 2. And these are your only solutions. There's 3 of them. Okay? The set notation is nice because all your solutions are there written for you. That one was pretty straightforward. I think what was important is the very beginning steps when you were using a double angle identity. All right, look how cool this one is. Example 3. Solve 2 times cosine squared of theta minus 2 times sine squared of theta plus 1 is equal to 0. Now, solve that for theta first over the interval 0 degrees to 360 degrees. And then when you're done with that, solve it for all solutions. All right, let's go for solutions that are between 0 and 360 degrees. All right, guys, my first initial thought is to factor out a 2. Let me say this, guys, and this applies to probably all of these equations that we've been studying in this chapter. Many times there's multiple ways to get to the solution. So by no means am I ever saying that what I'm doing and what I'm showing is the only way to solve the equation. So if you have another idea, go for it. You're probably right. So give it a shot. But I'm going to factor out a 2. Okay, that's what my instinct is saying to do. And then the cool thing about it is that inside of here, inside of the parentheses, I have an expression that reminds me of one of our identities. Cosine squared of theta minus sine squared of theta is the same thing as cosine of 2 theta. That's a double angle identity. So what I'm going to do now is I'm going to isolate cosine of 2 theta by subtracting 1 and then dividing by 2. Like that. So I subtracted 1, I moved the 1 over, and then I divided both sides by 2, which gets rid of this 2, not this 2. That's part of the argument. Okay? Now, we had a similar conversation a little while ago, and this is what we said. We know that we're solving for theta here. Okay, we're solving for theta. Now watch this. Theta has to be between 0 and 360 degrees. That's what the problem said. But right now, this argument is 2 theta. So when you consider substitutions for 2 theta, you have to multiply theta by 2 to get 2 theta. That means you should multiply 0 by 2, which is still 0, and 360 by 2, which is 720 degrees. What does that mean? That means 720 degrees is two trips around the unit circle, right, everybody? So be careful that you grab all your solutions and you don't miss any, all right? So here we go. Cosine is negative, right? Cosine of 2 theta is negative. And cosine is negative in quadrants 2 and 3, right? So when you take one trip around the unit circle, you'll find a solution in quadrant 2, and then you'll find a solution in quadrant 3, right? That's when cosine is going to be negative. Now, you and I know our unit circle very well. We know that cosine of 2 theta will be equal to negative 1/2 if 2 theta is equal to 2 pi over 3, right? Cosine of 2 pi over 3 is negative 1/2. Divide both sides by 2, and you'll get theta would be pi over 3. Cool? For quadrant 3, your solution for 2 theta would be, your substitution would be 4 pi over 3, right? Check your unit circle. Cosine of 4 pi over 3 is also negative 1/2. Divide both sides by 2, and you'll get theta is 2 pi over 3. Cool? Those are 2 possible solutions for our theta value. You know what I just noticed right now is that the equation asks for degrees. How do I know that? Because of this right here. They're telling you solve for theta in degrees, but I accidentally went for radians. Can I fix that? Of course. That's what this eraser is about. So I'm gonna you're gonna see me erase. Okay, everybody. I want to change this to 2 degrees. I guess I want to erase. Hopefully I can. There we go. Let me change these to degrees really quickly. Okay. Bear with me. Okay, cool. So we said cosine of 2 theta will be negative 1/2 if 2 theta is 2 pi over 3, which is the same thing as 120 degrees. That's 2 pi over 3. So dividing both sides by 2 gives you 60 degrees. Okay, so there's one answer in degrees, right? And then the other one was 2 pi is 4 pi over 3, which would be 240 degrees. That's 4 pi over 3. And when you divide both sides by 2, you get 120 degrees. All right, good. Now I have my solutions in degree mode. Okay, we're not done though, guys. Remember, 2 theta, we're substituting things in for 2 theta. And 2 theta has to be between 0 and 720. That means, so this is what you've done so far. Here's the visual, okay? I always go to a visual if I can, for those that understand a little better looking at a picture. So I see that for 2 theta, we're going to go from 0 to 720 degrees. So far, you've given that 2 theta is 120 and 2 theta is 240. All right, so then what you've given for 2 theta, okay, everybody, is 120 degrees, which is right here. And you've also given 240 degrees, which is right here. All right, those are the 2 values for 2 theta that you've given. Now remember, 2 theta, though, has to go between 0 and 720. So far, you've only given substitutions for 2 theta between 0 and 360, right? So this is what I want you to do. What is this? This is 120 degrees, right? Add 360 to that. What's 120 degrees? Here, let me label this. I think it'll be better. Oops. Hold on. Just a second. There we go. What's this is 120 degrees, and then this is 240 degrees. Oops. Like that. Okay, guys, I started at 120 degrees, and I added 1 full rotation. So what's 120 degrees plus 360 degrees? 480 degrees. That's right. So then 2 theta can also be 480 degrees. Now watch this. When you divide both sides by 2, you get that theta is, or can be, 240 degrees. That's another solution. Now watch this if you can, if it's not too hard to see. If you start at 240 and you go add 1 full rotation to it, what is 240 plus 360? 600 degrees, that's right. So 2 theta can be 600 degrees, which of course means when you divide both sides by 2, that theta is, theta is 300 degrees. Okay? So I don't want you to lose all 4 of your solutions. All 4 of your solutions are theta is 60 degrees, theta is 120 degrees, theta is 300 degrees, and theta is 240. Notice that all 4 of these answers are for theta, and all 4 of them are between 0 and 360. If we had not considered 2 theta, the interval for 2 theta, to be between 0 and 720 degrees, please notice we would have lost this solution, and we would have lost this solution, right? We would have only gotten these 2. So here's your final answer, okay? In set notation, 60 degrees, comma, 120 degrees, comma, 240 degrees, comma, 300 degrees. These are all of your solutions, all right, for theta between 0 and 360 degrees only. Okay, guys, now for the second part, we want to solve for all solutions. Now, look at the argument of the equation that we solved. The argument was 2 theta. Now, it didn't turn out to be, it wasn't 2 theta in the original question. Here, let me scroll up so you can see it. In the original, here's the original right here, folks. The original is here. It wasn't 2 theta to start out with, but with our substitution, we ended up solving for 2 theta, right? 2 theta. That's what we were solving for after our manipulations. So when we solve for all solutions, notice your argument is 2 theta, which implies the period, right? I'll just write P for period, is 2 pi over B, which is 2. So then it is pi. That's the same thing as 180 degrees, right? I forgot that we're in degree mode, right? 180 degrees. Now, Let me scroll up a little bit so you can see our solutions from the first part. Okay. Now look at this. One solution is 60 degrees. Oh, sorry, I didn't mean to do that. One solution is 60 degrees. Okay. This one is 60 degrees. Okay. And another one is, watch this, another one is 240 degrees. I'll talk about the other ones in just a second. Now watch this. Your period is 180 degrees. So watch this. If we start with 60 degrees, that's one of our solutions, and we move 180 degrees from there, we hit another solution, which is 240 degrees. If we go 180 degrees from there, we hit another solution. 180 degrees, another solution, because these are periodic functions. Another 180 degrees, another solution. Another solution. Another 180 degrees, another solution. Another 180 degrees, another solution. Another 180 degrees, another solution. In other words, I hope what I've really made clear is that why don't you just start with 60 degrees and go multiples of 180 degrees from there, and you'll generate all of your solutions, all in terms of 60 degrees, plus any multiple of 180 degrees. So what I'm trying to say is, what we can start right at our final answer like this: 60 degrees plus any multiple of 180 degrees times n, right? N is an integer. Okay. Now watch this. Now I'm gonna draw you another picture. All right, I've edited the picture to show 120 degrees and 300 degrees. Now remember, your period is 180 degrees. If I start with 120 degrees and I move from there, I add the first multiple of 180 degrees, I get 300 degrees, the other solution. If I go another 180 degrees, I get an answer that is coterminal with 120 degrees, which is another solution. Go another multiple of 180, a brand new solution, another solution, another solution, another solution, another solution, and so forth and so forth. So what I'm hoping to show you is that let's start with 120 degrees and then just move multiples of 180 degrees from there. All right? So in other words, we can finish off our solution by saying, our solution set by saying 120 degrees plus multiples of 180 degrees. All right? So this is our final solution set. Cool, you guys. Let's look at one last example, and then I think we'll be good. All right, solve the following equation over the interval 0 to 2 pi. Now, this is the equation that they want you to solve for. X, cotangent of 2x, minus cosecant of 2x, can you hear that motorcycle driving by? Is equal to 1, okay. Is equal to 1. Cotangent of 2x minus cosecant of 2x is equal to 1. Now, my initial thought, guys, is that there's a identity that puts cotangent squared and cosecant squared in a relationship. So my first idea is to square this thing so that I can use that identity to my advantage here. But before I square, I think it'll be better if I isolate one of these functions. If I either isolate cotangent of 2x or cosecant of 2x. I think what I'll do is I'll isolate cotangent of 2x by adding cosecant of 2x to the other side. All right? So then I'll have cotangent of 2x is equal to cosecant of 2x plus 1, like that. And then I'll square both sides. So I'll square this side, and I'll be very careful to square this side. Okay. When I square the left-hand side, that just means cotangent squared of 2x. All right. When I square the right-hand side, I get cosecant squared of 2x plus 2 times cosecant of x. 2 times cosecant of 2x, and then plus 1. Now, the cool thing is now I can replace the left-hand side using that Pythagorean theorem that I mentioned. This one here, cotangent squared of a plus 1 is equal to cosecant squared of a. That implies that cotangent squared of a is the same thing as cosecant squared of a minus 1. So I'm going to substitute now into my equation on the left-hand side. That means the left-hand side is the same thing as cosecant squared of 2x minus 1 is equal to all of this on the right-hand side. Okay, and I got it all. Okay, now this is the cool thing here. Notice that you got cosecant squared of 2x on the left-hand side, cosecant squared of 2x on the right-hand side, and so this whole equation is written now in terms of just cosecant of x, cosecant of 2x. I'm going to subtract 1 from both sides. When I subtract 1 from both sides, I get negative 2 is equal to 2 times cosecant of 2x. When I divide both sides by 2, I get negative 1 is equal to cosecant of 2x. Man, this thing started off to be a lot, and then it turned out to be not that much, right? If cosecant of 2x is equal to negative 1, that means sine of 2x is equal to the reciprocal of negative 1, which is also negative 1, right? What I used here, that's a double arrow, what I used there is the reciprocal identity. Now, I hope you're used to this now. We want to solve for x, and x is between 0 and 2 pi, right? But at the moment, we have the argument 2x. So that means 2x will be between 0 and 4 pi, right? When you multiply everything by 2. So remember that when you're substituting things in for 2x. All right. So here we go. Sine of 2x will be negative 1. Yes, it will, if 2x is equal to 3 pi over 2. Sine of 2x, will also be equal to negative 1 if 2x is equal to 7 pi over 2. There. Those are the two solutions that are between 0 and 4 pi. Now what I want you to do is a little arithmetic when you divide both sides by 2. Remember, dividing both sides by 2 is the same thing as multiplying by 1/2. This becomes x is equal to 3 pi over 4. And over here becomes 7 pi over 4, like this. All right? So these are proposed solutions. The reason why I said they are proposed solutions is because we squared both sides. So it's possible that that one of these is extraneous. So we should probably check our work here. So bear with me as I walk you through checking these two solutions. Now, the original equation is what you should be plugging these into. Okay, this is the original equation, and I'm plugging in 3 pi over 4. It gives you cotangent of 3 pi over 2 minus cosecant of 3 pi over 2. And supposedly this is equal to 1. That's what you and I want to confirm. Now, cotangent of 3 pi over 2 is just 0, minus, and then cosecant of 3 pi over 2 is equivalent to sine of, cosecant of 3 pi over 2 is the reciprocal of sine of 3 pi over 2. And sine of 3 pi over 2 is negative 1. And cosecant is the reciprocal of that. The reciprocal of negative 1 is just negative 1. I stuttered there. Sorry if I confused you. So 1 is equal to 1. This definitely checks out. What I would invite you to do is to plug in 7 pi over 4 and confirm that it checks out. All right, by now you should show that you should have seen that both of these check out. So your final answer, when I say they both check out, I mean that they both satisfy the original equation. So your final solution set is 3 pi over 4 and 7 pi over 4. All right? Cool, you guys. I think you've seen everything you need to see in this section, and I can hardly speak anymore. So this is the end of section 6.3, trig equations part 2. All right. I'll catch you in the next video when we discuss 6.4, which is equations involving inverse trig functions. 6.4 happens to be the last section of chapter 6. All right, cool. This is the end of 6.3. I'll catch you later.